Welcome back. So let's continue with graphs. So 1.2.1. So the first kind of subsection in the second half is about number of edges. In the complete graph, Kn. So let's try to figure this out. So when there's one vertex in the complete graph, K1, how many edges are there?
None.
0. What about 2?
1.
1. So what about 3?
3.
3. 4. Anyone?
6.
6. 5.
10.
Yep. So in general, if it is, let's say n, what's the number of edges is what we are trying to figure out. Does anyone have a guess?
And pick 2.
Why is that?
Because we need 2 vertices to make an edge.
Naomi, what do you think? Do you agree?
Combinations.
So what people say is the number of edges in Kn is equal to n pick 2. What's the formula? Isaac, do you remember? N pick 2. Olivia? Okay, which is 2. Yep. So let's kind of pick the n here. When n is equal to 5, so it would be 5 times 4 divided by 2. So that's 10. So it seems to be working. So the way the graph described it was very good. So remember when Kn, complete graph, what it basically means is there are kind of n vertices here. And then every pair of vertices has to have an edge. So because of that, the number of edges is basically number of every possible pair of vertices. So very good. So I didn't expect someone come up with the answer that quickly. So can I get a show of sign? How do people feel about the number of edges in a complete graph is n plus 2? Okay. So let's do it the difficult way. What's the difficult way of doing this? Mathematical induction. So S1, no, Sn is basically this statement. So S1 is definitely true. You put 1 here, you got 0, and this is 0. Okay? So now the second step of mathematical induction is assume S of k is true for some positive integer k. So what does it mean? So now let's look at the graph. Complete graph, okay, it's particularly bad. K, because it's also K, okay, K plus 1. So what you have to remember is for a complete graph with K plus 1 vertices, so there are K vertices, and then there's one more. Okay, so this is basically K plus 1 vertices. And for a complete graph, that means kind of every possible edges of this. So every pair of vertices is connected. Now, if we kind of do a circle here, how many edges were connected within the first K vertices? By mathematical induction, because we assume for the complete graph with only K vertices, this is the many vertices it has. So therefore, the total number of vertices in this kind of graph with K plus 1 vertices is basically apply the formula when n is equal to K, which is K times K minus 1 divided by 2. And how many new edges are there? That's connecting the K plus 1th vertex. Okay, because there are K vertices here. For a graph to be a complete graph, then that means this vertex has to be connected with every other vertices here. So then that means the total number of edges in the K plus 1 complete graph is basically this. Now the rest is you do a little bit algebra. If you survive the homework last week, then you basically quickly see this one is K plus 1 times K divided by 2. So therefore Sk plus 1 is true as well. So I particularly like this example of using mathematical induction, not because this is the easy way to do it. I think what Rafi said at the beginning was the easy way of counting what number of edges are. But one thing I keep emphasizing last week when we talk about mathematical induction is mathematical induction is not the way to only prove equation and formula. So there are a lot of difficult mathematics theorem about graphs, about geometry, about topology, where mathematical induction is what you need in order to demonstrate it. In fact, the theorem that I talk about, planar graph, is also proven by mathematical induction. Okay. So let's move on. To the next one, which we are going to do more definitions. So we're going to have more definitions. So definition 1. The degree of a vertex is the number of edges connecting to it. Okay. So let's say we have a graph A, B, C, D, E, and then F. So we usually use the notation D, small d, to denote it. So the degree of A is equal to, what is the degree of vertex A?
2.
2, yep. And the degree of B is equal to Daisy. How many edges are connected to the vertex B? 3. Good. So similarly, degree C is equal to 3, degree of D is equal to 2, degree of E and degree of F is equal to 1. Okay. Now this is related to the to one of the homework question. So the distribution of degrees of a vertex. So this is not a definition, but basically what we sometimes say is there's 0 vertex with degree 0. And then how many vertices do we have with degree 1 in this graph?
Which one?
This graph? 2. And then how many, and then we have 2 vertices with degree 2. And then we have 2 vertices with degree 3. Okay. So this is a distribution of the degrees. Okay. So let me see. Some more definition. So the definition is called a walk. Okay. A walk in a graph G is a sequence of vertices A1, A2, A3, etc. to AN, such that A1, A2, A2, A3, A3, A4, etc. are all an edge. And when this happens, we call it the walks, joins, A1 and AN. So let me give an example. This is a definition of something that is pretty intuitive. One, two, three, four, 6, 7, 5, and 8. Okay. So this is a graph, and a walk is basically say if I want to give you a walk, joining 1 to 7, and you basically say 1, 2, 4, 6, and 7, because this is an edge, this is an edge, this is an edge, this is an edge. So this is what a walk means. A walk is actually related to a lot of mathematical games. For example, if I give you a graph, can you basically write a walk, visiting every vertices just once? So this is kind of one of the mathematics games related to graph theory. So this is a walk. So let's give 2 more definitions of graph theory before we go to the last session. So 2 more definitions. Definition 3. A graph is connected if every pair of vertices is joined by a walk. So take a pause here. Can everyone show a sign about is the definition pretty intuitive? Or how do everyone feel about this? Olivia? Okay. So what this basically just means, every vertex is connected by some path. If you start from one vertex, you can always find a sequence of edges to go to another one. So it's connected. Okay. So the last definition 4. A component of a graph is a connected subgraph not contained in a largest connected subgraph. So this is the official definition, but I'm going to give an example, but it's basically, I'm just going to call it is the very intuitive notion of how many pieces are there in the graph G. So it's a very precise way of describing how many pieces are there. So let's do a class exercise. The first one, A, B, and C. How many components are there in here?
3.
How many?
3.
2, because this one is connected. So it's one piece, this one is another piece. So this is 2. So this is 2 component. A second one, A, B, C, and D. How many components are there, Olivia? 1. 1. Mm-hmm. What about the utility graph? How many components are there in the utility graph? 1. Remember, that's the one where 3 houses at the top, 3 utilities company at the bottom, and then you're kind of connected to everything. So this is 1, this is 1, this is 2. So what about K3? How many components are there in K3? Daisy?
1.
1. Okay. So last one. How many components are there?
2.
Rafi thinks it's 2. Anyone else? This one? Olivia, how many components do you think there are?
2.
Isaac?
2.
Naomi?
1.
So I failed to trick 3 of you. So it's actually 2. Because this one, I just kind of visually kind of tricked some of you. But it's basically this. Remember, crossing, whether it crosses or not, is an artifact of how good I am. Okay? When something cross, it doesn't mean they're connected. When you think something is connected, it has to have an edge. So because of that, there's actually no edge connecting these two pieces. So because of that, there are two components here. Okay, so last section of today. Does anyone know what the last section is about? It starts with the letter I.
Illustrated graphs.
Good guess. So it's the word that I could not pronounce. So it's isomorphism. Okay. So I'm going to give a definition of what isomorphism means. Remember in the first half of the lecture, there are two graphs. Remember these two? This one is 1, 2, 3, 4, 5. And this one is something like 1, 3, 2, 4, 5. I said, well, they are kind of not equal, which I agree, but it's a bit of a labeling exercise because the structure is basically identical. And I said, we would basically call this true graph isomorphic because they are practically, structurally identical, except the vertices just have different set of names. Okay. So I'm going to say that what it means is two graphs, G and H, are isomorphic. The way to write it is G a curly at the top and then equal at the top at the bottom. If first of all G and H have the same number of vertices, and you can map each vertex in G to one and only one vertex in H, such that whenever two vertices in G are connected by an edge, then the two corresponding vertices in H are connected by an edge as well. So I'll first give an example, and then I'll come back to ask how does everyone feel about isomorphism. Okay, so I need to draw this really carefully. So 1, 2, 3, 4, 5, 6, and set. Okay, can everyone see this one? So this one is called the graph G. And then I'm going to write another graph H. H that look like this. And the vertex is called A, B, C, D, E, F, and G. So this graph is called H. So the graph H actually looks a lot nicer. It's basically a loop. 1, 2, 3, 4, 5, 6, 7. 7 vertices. Just write a loop. And then there are 2 edges across it. Whereas this one, it looks really bad. Okay? But this is the reason about isomorphism. Let me just kind of tell you what the mapping is. A, if I map A to 4, B to 6, C to 1, D to 3, E to 5, F to 7, G to 2. So let's just count the number of edges first. How many edges are there on the right hand side? Can the girls help me count? And how many edges are there on the left hand side? Can the boys help me count? The number of edges. Nine. So 9 edges here. How many are there on this side? 9 as well. Okay, so at the very least, they have the same number of vertices, 7, and the same number of edges as well. So I'm going to read it out from the right hand side, and you have to tell me yes or no. Okay. So this is 4. This is 6. Is there an edge connecting 4 to 6?
Yes.
Is there an edge connecting 6 and 1? 6 and 1. I'm trying to see, okay, on this side, let's say there's an edge connecting B and C, and because B map to 6, C map to 1. Is there an edge connecting to 1 and 6 on the left hand side?
Yes.
What about 1 to 3? What about 3 to 5?
Yes.
5 to 7?
Yes.
7 to 2?
Yes.
2 to 4?
Yes.
4 to 5?
Yes.
5 to 6?
Yes.
Okay. Now let's regroup. Okay. We have the same number of vertices. We have the same number of edges, and whenever there's an edge connecting 2 vertices, they're kind of cousins. The 2 corresponding vertices also have an edge connecting them. So because of that, we can basically say now G and H are isomorphic. Okay. So there's kind of one homework question that will give you 2 graphs and ask you to figure out the mapping, why the 2 graphs are isomorphic. So the last part is not graph theory per se, so I'm just going to verbally talk about it. So graph theory, I think, was invented something like the 18th century. So there was a very famous I want to say somewhere in Europe, I think it's Austria, that there are basically 7 parts in the city, different parts are connected by a bridge. And there was a question about, okay, can you actually go to those 7 parts of the country, the city, without crossing any bridge more than once? So there was the kind of original graph theory question that was kind of talked about, that said that's the origin of graph theory. So graph theory basically is something that people did for fun for maybe 2 centuries. And then I think in probably the last 30 to 40 years, it became one of the most most lucrative subject. Basically, if you're good at graph theory, you'll get paid a lot of money. Can anyone make a guess why? So it turns out what happened is graph theory is the perfect description of networking in the world. When you think about each of these vertices, if each of these vertices is, let's say, a computer or data center, or let's say a cellular tower, it actually describes very accurately what people care about in computer network, right? You actually don't care about 2 pieces of node or server, how they're connected. The only thing you care about is, are they connected? So because of that, graph theory in the last, let's say, 20, 30 years, found a huge, most important application in, let's say, the internet or in computer networking. Now, obviously, there's also this kind of social network company called Facebook. Each individual is a person, and if the 2 persons know each other, you join an edge connecting the 2 persons, and kind of mining or analyzing that whatever billions of users the Facebook has, whether they are friends to one another, also became another huge kind of application. So it's another example of what the first reading about, pure mathematics. It was purely invented because someone thought it was fun to do, but over the century, somehow this is kind of found in the mainstream of the most practical branch of mathematics just in the last 20, 30 years. So I think that's it.